Okay, let's move in atomic structure. So hopefully you've read this or hopefully you remember this. So let's walk through what we already know. First of all, we're going to do kind of this table. We're going to talk about abbreviations as well as the relative charge and relative mass. But the abbreviations, the different ways that we can see it. So proton, if you have one H, a hydrogen, again, has an atomic number of one proton in the nucleus. A wave one would make it, in fact, just a proton. So in fact, we also have to add that plus charge in the upper left because that would indicate that there's no electrons there either. So that would be a proton. I know you're going to see this later when we start looking at acid-base chemistry. H plus is just a single proton, and there's a lot of problems there with that. But either way, that's what we look at. The atomic way or the nuclear way to say it is just a P, lowercase p, 1 indicates one proton, one, again, atomic number one, mass number one. Relative charge, a proton has a charge of +1. Relative mass. Overall, we say 1 AMU. Well, what is an AMU? An atomic mass unit. It's difficult to really express how tiny this value actually is. So an atomic mass unit, we use that just to simplify things for us because the actual kilogram weight of a proton and a neutron and electron is super tiny so we just talk about in relative terms to one another. So an atomic mass unit is based on carbon 12. So it's one AMU is 1/12 the mass of carbon 12 because it has 6 protons and 6 neutrons. So that is how we calculate an AMU. Okay, next up, neutrons. Neutrons, the atomic way to do it is, or the nuclear way to do it is, has 0 mass, 0 atomic number because it's 0, 1 mass number because it weighs 1, or just simply an N. We can represent it either way. Neutrons provide mass as 1 atomic mass unit, but do not provide any charge. So we ignore neutrons when we're actually talking about charges. And we're going to find out we pretty much ignore neutrons and we just go straight to the periodic table for mass anyway. Electrons, typically you see it just as E-, and that's pretty much all we're going to see it as. Relative charge of -1, and this is 0 AMU. It's like 1/1000th of a atomic mass unit, so there's no real point. Relatively, there is essentially no mass to an electron, although there is a mass to an electron, but in this case, there's no mass to an electron. So that is, those are our particles. So we have elements, we can describe them in a number of ways. And so this is generally the formula that you're going to see. In the center, we have the, actually, I'm not going to go that way, I'm going to go down. Okay. So in the center, the X, or the atomic symbol, is just, as we would expect, the element. The Z value is the atomic number, and that is equal to the number of protons. Those two things are eternally linked, right? So if I change the number of protons, I'm going to change what type of element I'm actually talking about. So Z and X, or Z and the element name, are always going to be the same. So what that means is if you have one, you don't need the other. So if I give you atomic number, there's no need to provide you with the atomic symbol. If I provide you with the atomic symbol, no need to provide you with the atomic number. And in most cases, you're going to get the symbol, and we're not going to really care about the number. The mass is the A. So this is the atomic mass. And I'm going to warn you right now, I'm going to use different terms. This is an atomic mass because we're talking about atoms, individual atoms. We're going to have things like molecular weight, which is the weight of a molecule. So we're going to add up all of the atomic masses. So you're going to hear molecular weight, molar mass, all of these different things are generally going to mean the same thing. But if we want to get very nitpicky about it, this is an atomic mass because it's specifically the atom, right? So if we were weighing a molecule, we call it a molecular mass. I mean, an ion mass or something like that. But atomic weight, molecular weight, molar mass, all of those generally mean the same thing if you just kind of understand what you're talking about. All right, so the atomic mass is the number of protons plus the number of neutrons. Okay, number of protons plus the number of neutrons. So that's the first indicator, or the first time we've seen neutrons come into play. All right, good. Actually, that's good. All right, the last little bit in the upper right-hand corner, and this is the hardest one for people to get for some reason, but it's the hardest one for people to get. In the upper right-hand corner, this is going to be our charge or oxidation state. You'll hear that as well, but that's going to be our charge. And the charge is equal to the number of protons minus the number of electrons. Okay, that's your total charge, protons minus electrons. If there are more electrons than there are protons, you should have negatively charged. Remember, protons are positive. Not confuse you. Protons are positive. Electrons are negative in nature. So if I have an equal amount of both, it's going to be neutral. It's going to be 0. So there's a couple ways you would see neutral. Something that is neutral. So if there's my element, you would see nothing, or you would see a 0 in the upper right-hand corner. Okay. Anything that's negative, you could see that. Or 1 minus. Usually we don't write the 1 because that's redundant. There's no point to put the 1 minus. If there's just a negative charge, that means it's 1 minus. But it is important. Another example is x2 minus. The number comes first. It should always be 2 minus or the number and thing, never -2. It shouldn't be -2, but you're going to see it in some places and you shouldn't. So yeah, and then positive is the opposite of that. But that's pretty much our makeup of our atom. Okay. So again, I just want to reiterate the whole idea here that I have protons and neutrons in the nucleus. I have the electrons around the outside. Okay, I'm sure you guys remember this is the version of the atom that you know. This is all of the mass is right there in the nucleus. Okay, so it's protons plus neutrons, and the electrons are doing their own thing around the outside. It's important. I drew it like this. This is the Bohr atom. We're going to talk more about this. It's an easy way to see it, but it's actually incredibly incorrect. The Bohr atom is a good way to look at things, but it's actually not how we should actually measure things. Yeah, and the last thing that I'm going to say, we're going to start doing charge eventually. The one thing that I want, the mnemonic, I hope you guys remember, is I'm positive I lost an electron. Okay, so I'm positive I lost an electron. That's going to be our, right, losing electrons. If you are losing electrons or they're less than, then you're going to be a negative charge, or I'm a positive. I'm positive I lost an electron. Okay, it's a decent way to memorize that or to remember that. Okay, so isotopes are atoms with the same number of protons but different numbers of neutrons. So isotopes, so carbon 12, carbon 13, carbon 14. Those are all of the versions that carbon comes in. Okay, and we know that carbon has 6 protons. Again, it's redundant for me to write that because we should know it's carbon, it's going to have 6. So the total number of neutrons, this carbon has 6, this 7, and 8 neutrons. They're all going to have different masses. These are all isotopes of carbon. We have 3 isotopes of carbon. Okay. Isotope symbols. Okay, so for these carbons, and this is kind of important because I actually did see this in a paper once. You will see something like, let's see here. Oh, that's 8. Let me finish that again because I just deleted it. There we go. So carbon 12. That is the proper way to write out carbon 12 to represent an isotope. If I just write carbon, I'm assuming that it's a mix of all of the naturally occurring ones, and we're going to talk about that. Or C-12. Okay, that's also okay. Or carbon spelled out 12. What's wrong with this one? Carbon 6. You guessed it. Saying carbon means it does have 6. 6 is not the mass. That's, first of all, doesn't, again, so this is my mass. This thing is not real. I actually saw someone do that for uranium. So it was uranium and then 92. I think it's 92, uranium 92, which is not a thing. You're not allowed to do that. It has to be the mass. Okay. All right. So the number of electrons in a neutral atom equal the number of protons in a neutral atom. So when we're dealing with neutral atoms, number of electrons equals the number of protons. Okay, so that makes sense. So if I have 5 negative charges, let me actually represent in a very simple way. If I have an atom with 5 negative charges and I have an atom with 5 positive charges, together, those equal 0. Okay, so they cancel each other out. If I add or if I lose an electron, I'm positive I lost an electron, all of a sudden the protons outweigh the electrons and we have a positive situation. Okay, good. So do these problems. All of these are going to appear as the homework. I'm going to, instead of creating new homework problems and these, I'll just put all of these in the homework. So you can certainly look through this and just do the homework. Or you can either do these here or you can do them on the homework. But either way, I want you to take a picture of this or submit that you actually did this stuff. All right. Atomic weights. So atomic weights, again, we're talking about atoms in this case. We identify these things. All right. We identify these things through mass spectrometry. So what you can do is you can actually divide a sample into its individual components. Okay, so here's an example of mass spec being run on zirconium, a sample of pure zirconium. Okay, so a simple process. Here's my zirconium. I hit it with some high energy stuff and I create ions. So I create some ions. The ions are here for a specific reason. They get accelerated. So I start shooting all of the different zirconium ions or atom that I'm looking at ions, and we have a magnet. So you can imagine if you don't weigh a whole lot, if you're not very heavy. Okay. So first of all, we have this magnet here. So when we eject these things, they should be positively charged because we're going to lose an electron. So these things are positively charged, meaning one side of the magnet is positive and one side of the magnet is negative, or at least one will repel the objects, the other one are going to attract them. So if you're really light, if you're a really light object, as you go through here, your speed is going to be greater because you're lighter. So you get pushed less and you're going to hit higher on the detector. Okay. So, or you're going to hit lower in the detector. If you weigh a lot, you're going to go slower and you're going to be deflected more. And so that's why you're going to be in that region. Ultimately, what that comes down to is every single one, there is a natural abundance of naturally occurring isotopes. So zirconium, for example, and I think that is our first example. No, it's carbon-12 is our first example. So carbon-12. So carbon in nature is going to have 2 forms that it comes in, carbon-12 and carbon-13. So if I picked up a sample of carbon here on St. Mark's campus, or I picked up a sample of carbon, I don't know, on the other side of the world, so a pure sample of carbon, because this is how elements work, it should have the ratio of 98.892% carbon-12 and 1.108% carbon-13. Okay, so the samples should always have the same percentage of different isotopes. And the same is true for our zirconium here. We have 1, 2, 3, 4, 5 different isotopes of zirconium. Okay. The number that you see on the periodic table, that is going to be what we call a weighted average of all of these things. So it's the weighted average, or the atomic weight is the weighted average of the naturally occurring isotopes of a given element. So how we determine that is this is exactly the same way that you're going to do the grade for this class, or for most classes anyway, is you are going to take the contribution from each isotope and you're going to combine them together to get your total average weight. So the isotope mass plus the fractional abundance. So if we take a look at the mass of a sample of carbon, Okay, mass of a sample of carbon. What we're always going to do is we're going to take a look at the mass times the fraction okay, so the mass of carbon 12 and carbon 13, because those are the two we have to worry about. The mass of carbon 12 is in fact 12 times the fractional abundance, which is 98.892%. Of course, I should turn that into a decimal, or I should turn that into a decimal, because we are in fact going to turn it into a decimal, because that's what we should do. So 0.98892%. Okay, good. That is comes out to be 18.184. All right. Good. And my carbon 13, mass of carbon 13 is 13 times the fractional abundance of 0.01108. Oh, I should probably get rid of this percentage. There we go. Equals, what do we got there? Oh, that's the wrong number. I'm sorry. Yeah. So if we do this math properly, let's see here. 12 times the 0.98892 gives me 11.86704. And actually, this shouldn't be, yeah, so I guess that's what we have for this one. What we have for this one is 13 times 0.01108, because that's the fractional abundance, 0.14404. In terms of sig figs, our fractional abundance has 4 sig figs. Our other fractional abundance has 1, 2, 3, 4 sig figs. Okay. So when I add these two values together, what do we get? So when I add those two up, 11.86704 plus 0.14404, I end up with a value of 12.01108. But of course, we're adding. I have 2 decimals. I have 4 decimals. So we need to round to 2 decimals. 12.01 should be our answer. So that's it. So 12.01 is my atomic mass for a sample of carbon. Okay. So again, it's just simply the mass number times the fractional abundance plus mass number of fractional abundance until you get through all of the isotopes. So you should give these a try. What is neon? What is magnesium? What element is this unknown here? And we'll take a look at these in class. Hint, hint, if you look at neon on the periodic table, you should see the proper mass. And for this one, you should compare it to the actual natural abundance and see where you're at. Don't look it up, don't Google it. That's kind of the antithesis of why we're doing this work. And then finally, let's just briefly talk about chemical formulas. So chemical formulas, C2H4O. This here is a molecular formula. A molecular formula has everything in a row. It typically starts carbon, then hydrogen, then alphabetically everything else. Okay, I'll say that one more time. Carbon, then hydrogen, then alphabetically every other element. But it is the simplest, it is essentially everything in there. There's a bunch of different versions of C2H4O that I could make. This is the simplest version of it. Everything is just kind of categorized, but it's the molecular formula. Molecular formula, nope, formula. There we go. This right here, we call a structural formula, because I am getting a little bit of information. The CH3 tells me that there is a methyl group, and we'll get more into the wordings like that, but this is a methyl group, it's on the end. So that carbon has 3 hydrogens attached to it. This carbon here has one oxygen and an OH attached to it. And as you learn more about chemistry, you kind of put these things together. Oh, this is a methyl group. This is a carbon with that right there. I know that group, that is an organic acid. So as a chemist, I recognize that it is in fact that. So we have the 2D version of it. I mean, I think that they call it a bunch of different things, but that's a 2D version of it. And this is known as ball and stick. Okay. And so the last little bit I want to talk about is the idea of an isomer. So here we have acetic acid, and the molecular formula, the structural formula, the 2D representation, 2D organic representation, and ball and stick. So all of these are different ways of representing the same exact thing. Some are more important. If I'm writing a paper, I'm not going to use the 2D in the middle of my writing. And in fact, I probably rarely use the molecular formula because it seems pointless, because it doesn't provide any structural information, which is usually important. So this is kind of the go-to. But if I'm trying to look at where reactions are happening, I'm going to look at this. If I want to look at spatial orientations, I'm looking at ball and stick. So there's a purpose behind all of these things. This gives me 3 dimensions, a little more than the 2D version does, because in fact it's 2D. So we got to talk about the term isomer. So an isomer is the same chemical formula. I shouldn't say chemical. What I should say is I should say same molecular formula. But different connectivity. So let's take a look. These are acetic acid and methylformate. Okay, so if I take a look, I'm going to highlight the carbons on the left, and I'm going to highlight the carbon on the right, because there's only 2 carbons in this whole thing. So in the acetic acid, carbon is connected to 3 hydrogens, and the other carbon is connected to COOH. But the methylformate, carbon is connected to 3 hydrogens, but then it is connected to an oxygen in between the 2. And we would actually write it like this. That carbon is connected as that. Okay, so notice that these carbons are connected to each other, and now the carbons are connected through an oxygen. So they're connected differently, but they have the same exact chemical formula or molecular formula. Okay, that's an isomer. They're same formula connected differently. And then we look at something like a structural isomer. A structural isomer is they are the same formula and the same connectivity, but they are different geometrically. Okay, so they're different geometrically. We're going to talk about what this actually means in like isomers and in more detail when we talk about a little more organic chemistry, but they're structurally very different. Okay, these things look the exact same, and in fact, they should be the exact same, right? This carbon has a double bond. This carbon has a double bond. Perfect. This carbon is connected to the same exact stuff. This carbon has double bond connected to a CH3, connected to a CH3. These exist in the same exact spot. So everything is exactly the same, but this is where the left and the right-handed thing comes in. This carbon right here is special. This carbon right here has a left or a right-handed version of it, and we'll explain why. It's a geometric thing. So one smells like spearmint. The other one actually smells like, I forget these seeds, but one smells like, I think it's rye. It smells like rye. So yeah, very different connectivities. chemistry is weird that way and also magnificent in that way. So just that one small, like left or right-handed makes one smell like, oh, caraway seeds or spearmint, which is very different than one another. So anyway, yep. So that's what we got. And that is all.